Hi, uh, this is the PowerPoint presentation of our term project related with the class Seismic Design of Reinforced Concrete Structures EQE 550, which we are the students of GEBZE Technical University. This semester is 2016 to 2017. The class instructor is Dr. Ahmet Anıl Dindar. My name is Mustafa Zorlu. I am the member of Group Red, and my group mate is Mehmet Hüdayi Baştürk. I will try to briefly present our term project, which is a 5-floor reinforced concrete dormitory building. Then we will do our assessment regarding performance level evaluations. Let's begin with the instructed parameters. Our parameters, first of all, our group name again is red. Our parameters are as follows. Our concrete class is C18. Seismic zone, which our building will be located on, seismic zone 2. The characteristic of our building is dormitory building. The building which will be used as a dormitory building. Then we have to design our structural system as a at the high ductility level. Then here we have the normal force limit for axial force limit for our column elements as 45%. Okay. Let's explain our summary information based on our instructed parameters. Number of floors, basement plus 3 typical floors, and we have a attic floor. Then typical floor height. In the original architectural drawings, the typical floor height was given as approximately 2.8 meter. However, for the dormitory buildings, as per the building by law item 8.202, minimum clear height for dormitory buildings from top of slab to bottom of the following floor slab the clear height shall be 3 meter. Therefore, considering our thickness of the slab, we have to design our story height more than 3 meter. In our example, it will be we have preferred as 3.25 meter. Okay, intended use of our building is dormitory building. Then material data is as like this. Our concrete, which was instructed by our teacher as C18, and our building is located in seismic zone 2. As you know, in our Turkish earthquake code, you cannot use the concrete class below C20 for the buildings to be constructed within zone 1 and zone 2, or within all seismically activated zone. You cannot use below than the C20 class concrete. However, our instructed parameters is C18. Therefore, we will consider C18 in our design stages. Reinforcement steel, it was not instructed. Then we have selected our reinforcement steel classes as per the requirements of our Turkish earthquake code. Then for longitudinal rebar it will be S 420. For confinement rebars it will be S 220. Modulus of elasticities for both materials are like this. Then our seismic parameters based on effective ground shear velocity is like the soil group should be B or C in accordance to the given effective ground shear velocity as per the we have selected these groups in accordance to our earthquake code. As per considering these soil groups, soil type should be Z2, then the characteristic spectrum periods are TA 0.15 and TB 0.40 seconds. Then effective ground acceleration coefficient for our building shall be 0.3 because of the seismic zone. It's again from the requirements of our Turkish earthquake code. Building importance factor is 1.4, which is a dormitory building, and again live load participation factor should be 0.60 because of dormitory building characteristic of our structure. The actuality level which was instructed as high. This is correct. Loads have been defined as per TS 498 code. Dead load, which covers the self-weight of structural elements, superimposed dead loads which we have studied for each floors considering the characteristic of building. It's in the range of 1.8 to 2.87. However, we have mentioned here as 2 to 2.5 kilonewton per square meter. Live load for dormitory building type of structure should be 3.5 kilonewton per square meter. Okay, let's continue with the architectural plan and formwork details. As we have previously explained that the height of each story are determined as 2.25 meter due to the requirement of the building bylaws item 8.02 for dormitory buildings. Then, to construct proper framing system, architectural plan has been revised slightly and new columns are added to 1/D and 6/D axis, and existing columns at B/3 and B/4 axis are shifted to intersection of C/3 and C/4 axis. You can see here at these two locations in the original architectural drawings there was no columns identified. However, to provide a proper framing system on this D axis, we have included these two columns. Then again on 3 and 4 axis, to provide a proper framing system on both 3, 4 and C axis, we have shifted these two blue colored columns through Y direction, and you see here colored with magenta. Then it became a very regular framing system rather than the previous one instructed in the architectural plans. You see we have a regular framing system on both directions. Then loads considered in design. At first stage we have determined the slab thickness in accordance to TS 500. As per our calculations, 12 centimeter thick slab has been found applicable at all floors. However, for stairs we have preferred 15 centimeter thick slab without further calculation, but based on our previous experiences. super dead load and live load on slab elements, which the building is a dormitory building, terrazzo tile, and will be applied on the floors. At the floor, the roof structure was located on floor and attic floor together. Then we have considered some super dead load due to roof structure. For typical and super dead load became 2.57 kilonewton per square meter on floor 4 and attic floor. Then live load is 3.5 kilonewton per square meter. However, for the typical floors below the 4th floor, the super dead load will not include the roof structure as it is the normal case. Then the partition wall loads and on beam elements has been considered in design as like this. On the following stage, preliminary design of column and beam members have been performed. As you may know, columns dimensions are determined in accordance to the axial force under load factor design, which is 1.4 gravity load of self and super dead load, 1.6 multiplied to the live load. We have the axial force on the columns. Then we have determined the dimensions of our columns. We have 3 typical columns, which first one is the 25 multiplied by 60, the second one is 40 multiplied by 40, and the third one is 30 multiplied by 60, which is centimeter. As per our calculations, based on the shear force acting on the beams, we have designed all main beams on frame as 25 multiplied by 50 centimeter, and continuing cantilever beams or framing beams are again 25 multiplied by 50 centimeter, and the all secondary beams, which are the perimeter beams, only subjected to the wall and window loads on them, these are 20 multiplied by 50 centimeter. Okay, based on our structural dimensions, we have modeled our building using the software ETABS as like this. We have the column member labels and dimensions you see, and beam member labels and dimensions you can see here. On the following stage, we have to define the seismic design load methods. For the buildings located within zone 1 and zone 2, considering our height of the building, we can use either equivalent seismic load method or mode superposition method. However, we will apply the mode superposition method in our term project building. To do this, we have to consider both methods to perform the sensitivity analysis. At first stage, model analysis has been performed, and as per the model analysis, we have here the as an example mode of fundamental period at buildings X direction. Our period is 0.55 second for X direction and 0.61 seconds for Y direction, and for Y direction mode 2, and for X direction mode 3 is applicable. However, you see here mode 1, which is a torsion mode, torsion effect, indicating the torsion effect on our building structure. which is the mode participation, is very sensitive applicable. Then we have defined the response spectrum function as per the given parameters. You see here two graphical indication of our response spectrum function. In the first one, seismic load reduction factor is not applied on the structure. However, on the second one, seismic load reduction factor is applied on the function. You see here we have prepared for high ductility level of moment frame structure, which was instructed in table 2.5 as R equal to 8 shall be applied. Why is it? Why this is R equal to 8? Because our structure, we previously explained, including only the beams and columns without shear walls. We could prefer shear walls here, but in this specific example we did not prefer to apply the shear walls on the system. That's why we have R equal to 8. Then on the following page you can see the application of seismic load method, equivalent seismic load method. We have the base shear acting on the structure at both directions, V x, V y. You see here the seismic weight of the structure. We obtained this value from the software model. We applied the procedure and obtained these values. Then we again applied the mode superposition method, which O is should not be here. Sorry for this. Mode superposition method is applied using the GEBZE software. At first stage we have defined the load cases data, EQX spectrum and EQY spectrum cases with the scale factor of gravitational acceleration values is the scale factor here, which the unit is millimeter square per second. Please attention here. And the response spectrum function could be defined in GEBZE based on our Turkish earthquake code, which is defined as Turkish seismic code 2007 here. Acceleration as per the seismic zone, importance factor, site class, and seismic load reduction factor can be applicable on the software. Then the resultant base reactions as per the mode superposition method, we have the base reactions here. You can see which are rather lower than the values base shear acting on the structure in equivalent seismic load method. Then we have to apply the sensitivity analysis between mode superposition method and equivalent seismic load method. We did this sensitivity analysis as per the requirements mentioned under Turkish earthquake code item 2.8.5. As a result of this comparison, all design forces obtained under mode superposition method shall be amplified with a factor of beta multiplied by shear force obtained under equivalent seismic load methods divided by the shear force obtained under mode superposition method. But we have some conditions to apply these sensitivity analysis, which are in case any of the A1, B2 or B3 three type irregularities exist on the system, beta should be equal to 0.9. If not, if these irregularities not exist on the system, beta should equal 0.8. Result. As a result of our sensitivity analysis, we have found that no irregularity, any of the irregularity do not exist in our structural system. Then we have applied the factor beta as 0.8. Then amplification factor we have obtained as 1.18 through building X direction. However, for building Y direction, no amplification factor can be applicable. Therefore, we at the following stage we checked the base shear forces with the amplification factor, and we have obtained base amplification factor actually is included in the scale factor as like this of load case data. Then the resultant base shear forces have been obtained like this, as you may see here. On the building's X direction, which is 800 approximately 40 kilonewton, and on the other hand for the building Y direction is approximately 880 kilonewton. Then we checked the story drifts of the structure, and under this most superposition amplified most superposition method earthquake loads, story drifts have been found have been found within the range of the limit required by Turkish earthquake code item 2.10.1. The limit is 0.02. However, our maximum value at both direction of the structure even do not reach the 0.01. Then it's okay. So we can proceed with the reinforced concrete design as per Turkish earthquake code and TS 500. Reinforced concrete design of the structural elements actually has been performed in compliance with the requirements of high ductility level performance requirements mentioned under earthquake code item 3.3 for high ductility columns and 3.4 for high ductility beams. We have performed reinforced concrete design of the structure using ETABS, because ETABS now can be applicable, is covering our Turkish earthquake code and TS 500 requirements. I mean, you can use the ETABS software to check your to design your structural elements based on our codes. At first stage, we have briefly indicated here the element forces considered in the design, and the second stage we indicate that the graphical outputs of our member forces to support the numerical outputs here. Then the detailed outputs actually have been presented in our report. As I told just before, reinforced concrete design of structural elements have been performed using ETABS software, and here you can see the snapshot of the design of any section, which in this specific one it is the 40 multiplied by 40 dimension of our column. You can here see that column elements details, section properties, material properties, design code properties, which are the reduction factors for concrete and steel, and axial force and biaxial moment design for mx pmm values, axial force and again biaxial moment factors here, shear design for both direction of the shear, then joint shear check, and strong column weak beam and strong column weak beam or weak beam strong column capacity ratios are indicated within the design interface. So we can proceed with the details of the reinforcements. As per the results obtained through the software, we have chosen the reinforcements, both longitudinal and transverse reinforcements. For transverse reinforcements, we have considered our minimum requirements of Turkish earthquake code. Then for the longitudinal reinforcements in beam design, actually we should not prefer more than the required because of plastic hinging methodology and strong column weak beam methodology. Why? If you choose much more than the required steel longitudinal rebar, you shall recheck your strong column weak beam conditions. Then again we applied the same method for our column design. We have selected our reinforcements, both longitudinal and transverse, their rebars. Details of reinforcements on column elements as like this. We have three typical column elements which will check the damage level of these elements in the previous following stage. That's why we have indicated here the details of these columns. Then again we have graphically supported our numerical results of longitudinal shear design used in the software which are clearly seen here. These are only example purpose. On the following stage we have checked the strong column weak beam condition. Again we performed these calculations using the ETEBZE software. ETEBZE software clearly considers our requirements mentioned under Turkish earthquake code item 3.3.5, and for joint shear capacity check it considers our Turkish earthquake code item 3.5 as like this. We know the details. And here are the again specific examples for results of column and beam sections have been found sufficient. It says here, as per the results, all column and beam sections have been found sufficient in respect of strong column weak beam check. You know the limit for strong column weak beam check is 1.2 as per our code requirements, and you see the associated values are higher than the minimum limit. Okay, in the final stage we have been instructed that the first floor beam elements and basement floor column elements on one direction should be checked in respect of damage level analysis. We have performed these analyses considering the item 7.4 and item 7.5 and Annex 7.7a of Chapter 7 of our Turkish earthquake code. As per our aforementioned code, building importance factor shall be applied as equal to 1 for all type of buildings in these damage level analysis. In addition to this, as required by Turkish earthquake code, item 7.5.1.2, seismic load reduction factor shall be considered as equal to 1. Then another important point is that in doing damage level analysis, reduced flexural rigidities of structural members shall be considered. You see here, as per the instruction, damage level values will be calculated on one direction of the lower story. Then we have again, considering the symmetrical condition of our structure under mod superposition load under y direction EQE spec loading, which is load case EQE spec, we have performed axis 1, axis 2, axis 2 slash and axis 3 structural elements. As you see the label names here, we performed this damage level analysis. In doing this, at first stage we have determined the reduced flexural rigidities, which for all beam elements it should be 0.4 without any further calculation. However, for the column elements, we have to consider the actual load again on these elements. The actual loads from the combination of dead load plus super dead loads plus the live load multiplied by the live load reduction factor, as required by the code again. Then we have to revise this response spectrum function, considering that our seismic load reduction factor should be equal to 1 and importance factor of the building should be equal to 1. Resultant base shear forces have been obtained as like this, which are much more higher than the divided values in the previous stages. Approximately on building XY direction, both building X and Y directions, these base shear forces are approximately the same because of the model analysis. Then we have performed the evaluation of beam members. Both beam members and column members have been evaluated in 2 steps as required by the Turkish earthquake code table 7.2. First, we have to determine the impact capacity ratio associated with the damage zones. Some interpolations have been performed here. We have considered the capacity of the section as per the our longitudinal rebar dimensions, which we previously defined on the section, and here's some reinforcement ratio should be determined. At the following stage, we again performed our impact capacity ratio. We have determined impact capacity ratio. We have calculated this ratio based on the moment acting under earthquake loads divided by the excessive capacity. Then resultant damage levels have been obtained like this. Approximately 60% of our beam elements remains within the GV zone, which is slightly over the MN zone, which will be explained in the following stage as a conclusion. For the columns, we again performed in 2 steps. However, for this we have considered table 7.3 of our Turkish earthquake code. Then we determine the impact capacity coefficient. Then as per the in accordance to, let's say, in accordance to the moment and normal force acting under earthquake load and excessive capacity ratio, excessive capacity of the section, we have calculated the resultant impact capacity coefficients. As per these coefficients, we determine the damage level of our section you see here. For the columns, we have to consider the 2 points. One is point D here and one is point ED here. Let's say starting points are the forces, moment and normal forces obtained under gravitational loads, which is the combination, no combination, only the load case under dead load, super dead load plus live load multiplied by load reduction factor. And the second point is the combination of both starting point moment and axial force plus the moment and axial force obtained under earthquake load. Then the intersection point here, which the PM curve which the line intersects the PM curves at some point. At this point means the capacity of this section in respect of moment and normal force. Considering this capacity of the section, we can calculate the excessive capacity of the section. Then we can compute the impact capacity coefficient. Then we check the story drift for performance evaluation. It's found reasonable, and in respect of story drifts, building remains within minimum damage zone at both direction of the structure. So, conclusion: building seismic performance level as per Turkish earthquake code, chapter 7.7. As per the story drift check, subject building remains within the minimum damage zone. However, for the beam elements, it is foreseen that approximately 60% of the beam elements remain within the apparent damage zone. However, the other beams, which are six of total, how to say, we analyzed 16 beam elements. 10 of these within apparent damage zone. However, 6 of these remains within minimum damage zone. On the other hand, for the column elements, only the 18% of the column elements remain within the apparent damage zone. However, the other column elements satisfy the minimum damage zone. That means strong column weak beam condition is satisfied. Conclusion: with reference to the conditions mentioned under items blah 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 of our earthquake code, basement floor and first tier structural elements satisfy the life safety performance level on the building Y direction that we can conclude. At the end of our presentation, we check the bill of quantities, and doing this we ignored the slab element quantities of slab elements in respect of both concrete quantity and reinforcement quantity. So, considering only structural members, you can see total consumption of concrete is 123 meter cube of concrete. Then rebar quantities as like this, approximately 10% 0.5 tons of longitudinal rebar, which is the class of S420, and 8 tons for confinement rebar, which is the class S220. In the unit rebar consumption per concrete quantity can be calculated as like this, which is resulted as 150 kilogram per square cubic meter, let's say. If in the further stage you can consider the slab elements quantities as per our past experiences. 40 kilogram per cubic meter reinforcement consumption can be considered in the median. Then the resultant consumption will be decreased to between 100 and 120 kilogram per cubic meter. That's all we can conclude. Thank you for listening us. You can check our report in details for our design assumptions and let's say our considerations. Finally, I'd like to mention about our modeling software. Modeling briefly, which is a PDF document. At first stage, material properties has been defined as like this, both concrete and reinforcements. And the following stage, frame section properties have been defined, considering the concrete covers and both longitudinal and confined rebar classes, both for beam and column elements. Response spectrum function has been identified as instructed previously. Mass source data. In mass source data, self-weight of the structural members plus super dead loads plus live load with the participation 0.6. Then load patterns have been identified as like this, and the load cases, load combinations as per the Turkish seismic code and TS 500, which one example is like this. Then we have defined the diaphragms of the floors, which we consider that all floors have been reacted as the diaphragm slabs. 3D indication of our model is like this, and plan views of beam and column elements, and beam labels, column labels, and sections we identified. On the following stage, you can see the load assignments. Both the super dead loads and live loads have been assigned on the slab elements as like this, and partition wall loads have been included on the associated beam elements. Diaphragm extensions have been identified on the slab at each floors. And finally, you can see the concrete frame design preferences for TS 500, which includes seismic zone parameters. Thank you again for listening us.